Okay, hello everybody. I think I'll just continue with my discussion from last time about parton densities. So this is part 2. And I'll just start off where I left last time. We had gotten this definition with a one subscript because it's my first suggestion for a definition. It's the expectation value of a number density, and we argued that it was indeed a number density up to this overall factor of the proton's energy. And we understand it in terms of the underlying creation and annihilation operators that you see in quantum field theory. So here it is, and we still have quite a lot to do with it before it becomes something familiar, something useful. So at the very beginning, I said that one of the issues is that this state, the hadron state that's coming in, is not generally an exact eigenstate, and especially the quarks inside of it aren't going to be in eigenstates. They're in a bound state. They're not going to be in momentum eigenstates, that is to say. Whereas these creation and annihilation operators, they act on the vacuum and on momentum eigenstates, of course. So one of the things we can do is replace these states by wave packets. Actually, I always like to start with wave packets when I'm ultimately referring to physical external particles. It really helps us keep track of what exactly is going on. Sometimes it's a little bit redundant, but I still think it's useful. So I'm going to do that on the next page. Actually, I'm going to pause and just remark that actually all of this that I'm discussing, these steps here, well, remember that it's all for a free quantum field theory. That's how I started out. We're going to set aside the complications that come with interactions. Okay, and just look at the free field case. So this P, for example, I could prepare a state that just consists of 3, or however many I want, but if it's like a proton, 3 free quarks, all moving with, say, exactly the same momentum that all add up to the momentum P of the proton. So actually, I think that even all of the steps I'm doing here would apply if we're talking about a non-relativistic type of system. So you can think about non-relativistic particles here. And since we understand non-relativistic particles just from non-relativistic quantum mechanics, that might be useful to keep in mind. Okay, but anyway, let's go ahead and construct these wave packets now. So I'm going to define a new state, this ket vector here, labeled by a P, again, for the momentum of the incoming hadron. But now I'm going to say that it doesn't have an exact 3 momentum, but it's a spread out 3 momentum. Okay, and that means that I can localize it into a bunch, which of course in a real experiment, that's what would be happening. So here is, on the right side, a sum over a bunch of momentum eigenstates. I'm going to use underline a kind of foot on the P, which I'm labeling here as P prime as a dummy momentum. The foot here is going to say that this is a momentum eigenstate, an exact momentum eigenstate. I've got some wave function that I'm calling capital F, and we integrate over all these different possible P primes, all these different possible 3 momenta. So if I looked at the components of 3 momenta, it might look something like what I have in this figure here. It's bunched around some central value. Well, let's say that the P inside of this ket vector on the left is labeling the central value of this propagating wave packet. Okay. And you could even, if you want to be very slow and pedantic, write down an actual wave packet like a Gaussian or something like that. And we've got the relativistic normalization and so forth. I'm going to let delta be the width of this wave packet. And of course, ultimately what we want to do is say that delta is very narrow relative to the range of possible overall momenta of this particle, this incoming particle. Finally, with regard to this wave packet, let's let the wave function be normalized. Okay, so the normalization condition is here, which means that if the peak of this distribution becomes very, very narrow, approaching 0, then the square modulus of f needs to go to a delta function up to these normalization factors. Okay, so let's put that aside for 1 second. Well, we're going to go back to our F1 definition that I started with way back here. And instead of using just some generic P, let's use the specific state that I've constructed here, this wave packet state. I'm just going to put that in. And now here's the definition. It's actually maybe a slightly different definition if you want to be very pedantic from what I had back here, because now I'm defining it as a limit as delta going to 0. But anyway, here's our definition written in terms of the wave packet and as the limit as delta goes to 0. Just here. Now I'm ready to substitute stuff in. Okay, so first of all, I've got the expression that I just wrote down for the wave packet. I'm going to want to plug that in. And once I do, I'm going to have momentum eigenstates here. So that will be perhaps an improvement to working with what I started with today. So let me actually just copy and paste this over here. So we can substitute that in here. And now also remember that when I started out last time in the previous lecture, at the very beginning, I derived these relationships between the creation and annihilation operators and the actual Dirac field psi, right? And I said that I'm looking ahead here and thinking about, at some point, I'm going to want to re-express the definition in terms of psi. So now we're actually ready to do that. And since we are, let me also copy and paste this onto the new slide. And what we can do is plug B in over here and B dagger in over here. Can maybe pause the recording and go through these steps yourself, and then maybe we can compare our results. It's useful to go through this slowly so that once we get the definition for the PDF, it's going to have various factors and pieces. We can trace all the way back to the very beginning, to the fundamentals, and see where everything is coming from. So here's what I get. I'll maybe step through what's going on here. Okay, now you see that the bra and the ket vectors are the P prime and the P double prime. I'm using a prime and a double prime because now I've got two momentum dummy variables that I have to integrate over. Okay, because I've substituted this in here, I have to do another one. Well, I've substituted this one here, and I have to do another substitution for the bra vector, and that means I have to have another dummy variable, which I'm going to call P double prime. And that's what you see here. And now I've got the integration over P double prime. I've also got the integration over P prime. They come with their respective Lorentz invariant phase spaces. So yeah, here's the P prime integration. By the way, I've got f of P prime, that's the wave function coming from here. And then for the bra vector, I need an f star because it's the Hermitian conjugate wave function. And now I'm also substituting in the B and the B dagger. So we can look at these expressions. Here's the B, and there's an integration over a three-dimensional coordinate region. There's going to be another one from the B dagger. And so I'm going to need two dummy coordinate space variables there. And what I'm using are W vector and Z vector. I've got the 1 over square root 2 EK and the 1 over square root 2 EK coming from those. Those just combine to give this. I've got the sidebar from the B dagger here. Okay, everybody should be able to see where everything is coming from. important thing is I've got the exponentials here. They show up as the e to the w vector dot k vector e to the minus z vector dot k vector here. Anything else to remark on? Don't forget the gamma zeros and the u bar and the u. Okay, we should all be able to trace back to where those came from, right? And remember, we have to carry around these exponentials that I mentioned here that basically convert between the Heisenberg and Schrodinger pictures. Oh, and don't forget the overall energy of the proton, EP, sitting right there. Okay, next we can translate these fields in coordinate space. So this is what I've just done here. And all that does is it introduces some extra exponential factors to implement the translation. So this is how we do coordinate space translations. By the way, in principle, I should be carrying around something with the zeroth components as well. But remember, I've got this factor that can convert these fields back into momentum space Schrodinger operators. And so they'll end up just canceling out in the end if I carry them along anyway. So I'm not going to worry about that. Okay, now I can just substitute everything in. If I substitute in those translations, then I get those exponentials involving p prime and p double prime here. I've still got these ratios of the energies floating around. Don't forget those. Right from here, and then this E right here. Okay, I've gathered this exponential here. Now all the steps that remain are just to simplify this expression. It's worthwhile to go through slowly as usual. We can change variables from w vector to another three-dimensional vector I'll call y vector, which is just w vector minus z vector. So that will just make the argument here a single y, and the exponential here will be a y vector. I can integrate overall this z vector, and when that hits this exponential from the translation, that just gives me a delta function that sets p double prime vector equal to p prime vector. And then once I have that, I can evaluate the integral over p double prime. That's nice because now these states are going to have the same p in them. They're both going to be p prime. And the expression simplifies to what I have here. Since the p prime and the p double prime are equal to each other, this product of f and f star just becomes a squared modulus of the wave function. So f p prime squared. And I can take the limit that I want to take, namely that the width of momenta involved is very small relative to the momenta involved in the collision. So I'm going to take delta going to 0, and that reproduces me a delta function that sets p prime ultimately equal to p vector. And I'm almost there. So I just substitute that in up here and evaluate the p prime vector delta function. And here we go. Now, note carefully how I've arranged the different factors. I've put one of the 1 over factors of 2 here, one of the 1 over the factors of 2 here, because, well, I'm just setting it up so that the expression looks as close as possible to what you see in the textbook for Parton density once we get there. Now I've got the u s and the u bar s inside here, and if I sum over all s's, that just becomes, as you know very well from textbook identities, k slash plus the mass of the quark. Okay, now I'm going to make one more change in definition before I end today's discussion. to see why, first notice that I've still got the 4-dimensional k dot y up here. So there's a k0 in that exponent. But the integral is over 3 components, the 3 spatial components of y. And the 0th component of k is, of course, not independent of the 3 momentum, okay? Because remember, we're working with a free field theory. So all these particles are on shell, okay? They all obey the relativistic dispersion relationship. But I could imagine that I want a parton density that's not a density in 3 momentum, but a density in 4 momentum. Okay, here it's not a big deal because I know the relationship between 3 momentum and the energy. But if I imagine going to a more general situation, perhaps turning on interactions at some point, then I'm going to have all 4 components that can vary depending on the dynamics of the theory. And so it'd be nice if we have that to start out with, it, a 4-dimensional probability density. So let's actually see how to do that. Well, I'm going to make another definition here that I'm going to label with a 2 subscript. And now note that the argument is a k without any vector symbol on top. And I'm going to define it this way. Maybe I need to go in and put 3 lines here because I'm taking this to be a definition. I'm going to define it as the definition that we just constructed for this dn d3k vector operator. But I'm going to multiply it by a delta function that sets some general k0 equal to k0 prime. And we'll say that k0 prime is this relativistic dispersion expression. Okay, it's kind of silly to do this. It's just making a statement that k0 has to follow the relativistic dispersion relation in the form of a delta function. By the way, I'm also putting factors of 2 pi because if I organize them this way, it'll turn out to be useful. And be maybe a little bit mysterious, but I'm putting in a factor of square root 2 here for reasons that will become clear in a second. But for now, just take this as a definition. That's just an overall numerical factor that I'm including. And then I can use the fact that I can express this delta function as an integral over some 0th component in coordinate space, a time component, dy 0 prime, and an exponential factor like this. So this just gives me back the delta function. And note that this object that I've defined here is really a density in, it's a density in k0 over square root 2. So if I integrate over all k0 over square root 2, I get back the density in 3 momentum with k0 set equal to its appropriate value. So what I've done is just trivially re-express the 3-vector density in terms of a 4-vector density by using a delta function and a relationship between delta functions and integrals over exponentials. That's all I've done here. You can check what I've done here is correct. It has the properties of a 4-dimensional density now. So in other words, F2 is the same definition that I had before, but now dn is differential in the 0th component of k as well as the first 3 components of k. It's differential in the energy of k as well as the 3 momentum. Of course, all of this is up to these, for now, somewhat arbitrary looking overall factors that I've included by convention. Okay, so this follows from the previous line. Okay, I'm almost done for today, but Before I completely finish, maybe comment on these factors. Notice that all I've done is said that I can make a differential not just in k plus, k minus, and k perp, but I can take k plus and divide it by this constant factor here and call that a different variable. Here I'm going to call it x. It's going to be defined to be the k plus component of momentum divided by square root 2 energy of the proton, energy of the target hadron I'm talking about. Okay, again, this is still sort of arbitrary seeming, but it'll transition very nicely into the standard definition once we get there. Now I can take this F2 that I just defined and use the previous F1 that I constructed to make a number density in 4-dimensional momenta. So we can take that result and just put it in a box. Now I'm making the argument of F2 to be, well, I'm writing out the individual components of K, but for the plus component, instead of using the actual plus component K plus, I'm going to say, let's make it argument this X down here. Since it's now differential in X, K minus, and K perp, we can do that. So here is the final result for today that I've got right here. Now, how did I get this expression here? Well, all I had to do was substitute my expression that I derived for the number density in terms of 3 momenta down into this expression for F2. And now I just get another integral over a 0th component in coordinate space, along with the factor of 2 pi here. And so I get the same definition that I had before, but now there's an integral over 4 components of y and divided by 2 pi to the 4th. And the exponent now contains a k0 that isn't necessarily, in general, going to satisfy the relativistic connection to the 3 momenta, the connection for a free particle. Okay, so then you can check that when I integrate this over k0, I get back to the original definition, the 3-dimensional of the 3 momentum number density. We have what we need now. We have a definition for a parton density that really is a number density meaning particles per volume of 4-dimensional momentum. We take the expectation value between these p's, which, well, the way we did it was to take the limit of a narrow delta, a narrow width wave packet p. And now we have something that we can work with. For those of you who are familiar with this, this is starting to look like the definition that you've probably seen 1,000 times before. Still a few things that we need to do, but we're getting closer. So I'm going to end now, but next time I'm going to talk about how we need to approximate this expression. Specifically, we want to ask what happens to this kind of density if we're looking at it in a frame where this hadron, this proton, is moving at near the speed of light. Is there a way that we can approximate it that makes it even more useful for us? Okay, I'll pick up on that next time.